So we're going to look at the properties of light. I guess the first thing is to review waves. And really to be aware that it is a disturbance in a medium that carries energy. I feel like that's sort of the main point with waves, that it's not necessarily the medium itself that moves, right? So if you look at something like, someone sending a pulse, like a wave pulse down a rope or something like that, right? You pick any point, and in this case right now, it's sort of this point right here that's disturbed. That point is moving up, right? It could be, if it's more like this other one over here, like this point here, could be moving up and down, but it's just that point that's moving up and down. And even if it is moving side to side, right? It's generally its sort of equilibrium position is unchanged, right? It's just sort of the energy that's moving through a medium that we describe as a wave, and it may take the form of elastic deformation, that's this stuff here, variation in pressure, electric or magnetic intensity, electric potential, or temperature, right? There's energy can be transferred in any of these ways, and that would be, it could be considered a wave. Periodic waves, so anytime we talk about something periodic, we're just talking about something that is repeated at regular time intervals, right? That's what makes it periodic, and you usually get those nice sine function graphs and whatnot out of those. The different types of waves, and this is just sort of general. Longitudinal waves, in this case, is the disturbances are in the direction of motion. So if you look at something like sound waves, you've got, like, I'll just be a little general. I don't know if you can see, these are like your air particles or whatever. But remember, as sound is moving through air, you get these, right, sort of high pressure areas. You get stuff like this. Sorry, that looks bad, but you get the picture, right? You had what we call like condensations and rarefactions, and amazing that as you're talking and sending stuff out in different frequencies, it's actually this that's happening in air. So in this case too, the wave is traveling in this direction, right? This is the direction of motion. And the motion of the particles, though, is in this way as well, right? If you looked at here, we've got motion of particles. And you can see, right, it's in the same direction of motion. But in this case, the particles are just moving back and forth. Their net or bulk motion is not in the direction of the wave, right? The other more popular one is the transverse wave. This is just like the string or rope that we saw up here. These would be transverse waves. This is when the disturbances are in the direction perpendicular to the motion, right? So in this case, the wave there. This is the direction of motion or direction of wave. And again, you can see the particles here are moving up and down. Now, just to mention, the other type we look at is like a torsional wave. These aren't very common, I don't think, but they're technically, in this case, you can have sort of a twisting motion. So I always think of for a torsional wave something like a wet dog when it's shaking all the water off of itself. It's sort of, if the dog is sort of here, I don't know, right, it's sort of shaking itself right back and forth in this way. Perhaps a maybe slightly better example might be if you ever see like those tires at the park, because I got a kid I take to the park right now, so you see maybe they've got one of these tires right here, and it's chained up above, so it's got a few points here where it's chained up to something above. You could take this, and now you don't want to do this too much, right? You don't want the amplitude to be too strong to actually see this, but if you twist it just a little bit, and then let it go, you'll see it just rotate back and forth, just sort of twisting. Um, you probably experimented more with the interference, and this is with transverse waves. As I said, it's the most popular. It's mainly what we'll deal with, particularly with light, because it's generally a transverse wave. And you can sort of see like this really interesting phenomenon, right? If you look at constructive interference here, we've got this is just showing you, here's two waves headed toward each other, right? They're both crests right now, as we say, right? They're above the equilibrium position. And then when they interfere, that's the next one right here, which has already got a circle, right? So you actually see superposition. See, as they're going through each other, the amplitude is twice what it is at that point where their two maxima are passing each other. And that's constructive interference. On the other hand, we get destructive interference, which to me looks really, really cool. If you've got two waves like this, and this, obviously they've got equal amplitudes, they're going in opposite directions, and this could just be, waves, pulses on a string sent from two different sides. One sends a crest, one sends a trough, person, I mean. And then while they're passing, right, you get this really cool effect right here where it looks like no wave at all. Right? You look at that for an instant and you don't even know there's actually energy passing in opposite directions, right? It just looks like nothing, but it's not. And then after, sure enough, right, you can see they've passed right through each other, and now they continue on as if, the other one hadn't even been there. So that is interference. And it's just a really important thing to note, right, that they do interfere. However, right, it's you look at the amplitude at any point in time, and it's just add the two, right, whatever they are at that moment in time. And then after, like I said, no effect. If we want to look at the velocity of a wave, right, how far is it going? Sorry, I did see that question. No, generally we wouldn't look at these as vectors. You sort of could, like you do have a direction, but usually everything is either like in the direction of motion, like the longitudinal wave, or it is perpendicular. So that's sort of just part of the phenomenon. So you don't really have to look at angles or break things into components. So that kind of helps, but yes, it does have direction, but we don't really have to worry about all the vector stuff. So we're looking at the velocities. Let's take our little transverse wave up here. As you can see, we know velocity is delta x over delta t, right? How distance over time. And so you want to know, again, think of this as the energy moving or whatever, right? We know it goes one wavelength, which we're using this Greek symbol here, lambda, in one period, right? So t down here represents big T. We've used it before. It's the exact same thing here, right? This is a period. I probably wrote it below, but... And this is up there, you know what that is. So you could write it that way as lambda over capital T. Or since frequency, remember, is just the reciprocal of the period, right? It's the number of cycles per second, not how many seconds it is per one cycle. You could write it as V equals F lambda. That's probably just I don't know why I always found that particular one very memorable. Or just lambda over T, whichever works. I guess I would write down both. And this part, so we want to look at what light is in a little bit of detail. And I always just find, we can sort of save it. We can do all this stuff. Well, is it a particle? Is it a wave? And we'll get to that. I'll go over the debate and the history and all that later. But really, like, I feel like just understanding kind of what it is or what we do know before looking at the particular, or, picking a side or putting it all together. Let's suppose it is like just a particle. We're looking at it that way. It's very unique. Let's call it a photon. I don't know. So as it moves through space, like what happens? If there is a part, if there is a thing, what's sort of happening, right? So this is supposed to sort of represent my particle. And it's got some velocity here. right? It's moving in that direction, let's say, directly to the right. What's kind of special about this? Well, as it's moving, and this is just sort of representing where it is over time, right? In a little bit of time, it's going to be in this first position here. And suppose we had some sort of detector here. What we might notice is that this thing has an electric field in this direction. Right? We could sort of draw it like this or represent it like this. Yeah, that's about what I would do. And then a little bit later, if we're measuring it, or just as it moves, it's got a little bit of electric field, but it's not as strong here. It's still in the same direction, but it's not as strong. And then if we measure it just past that, we see no electric field. Now we measure it at the next spot in time, and we see, oh, it's actually got an electric field that's directly down. So just for simplicity, I'm drawing it this way. And then a little bit later, right, you can sort of see what's going to happen. It's down. And then not as much. And then nothing. And then we measure it here, it's up. And then it's stronger. Right. And this is sort of, as we're looking at this, electromagnetic radiation. And what does radiate mean, right? It just means to give off, right? It just means something comes out, right? And so we can look at it as, well, something, whether we're seeing it as a particle or a wave or whatever, as this thing is moving through space. If we have detectors all along its motion, or just underneath it here, we might notice this fluctuating electric field. And this continues ad infinitum, as it continues to go, unless it gets absorbed or something somewhere. We tend to see this. And so a way we might draw this is like this. You can already kind of see just from what I drew up here. Right. You're going to see a field like this. And that's sort of represented a little bit more by this picture here in 3D. Do note, and this is one of those little things sometimes people miss, but it's very important. The direction of propagation, right, is the direction of this big arrow here, right? That's really, see this in 3D, right? This is happening three-dimensionally. The direction of propagation is that way, right? That's the way the wave is moving. That's the way the energy is being transferred, right? But the electric field is 90 degrees to that, perpendicular, right? The changing electric field here is up and down. You can see here this, which is sort of drawn in blue. So it's perpendicular to the direction of motion, right? And the exact same thing is true of the magnetic field. And you can actually figure out what this magnetic field is, or where it sort of comes from, if you go back to electromagnetic induction, right? That if you have a changing electric field, that produces a magnetic field, right? And vice versa. So this really goes to the fact that electricity and magnetism are sort of linked. They're really fundamentally the same force. So that's why they work together. And they're always perpendicular to each other, right? So the electromagnetic wave is changing as the wave propagates up and down, and the magnetic field here would be changing perpendicular to that wave, right? So it would be sort of side to side. But both of them, their fields at any point in time, unless they're like zero right here, they're perpendicular to the direction of propagation of the wave. And that's really important to kind of understand, right? As the wave moves this way, right? Long, right? So this is a small wavelength up here, right? This is something that is very high energy. It's going, back and forth or up and down very high. The long wavelength, same speed, right? C, but low frequency, less energetic, and a longer wavelength. So just sort of understand the connection between wavelength. That's always one of those backwards ones you got to just sort of remember. Reflection, you're familiar with this. We've all looked in a mirror, so you somewhat understand it. someone was telling me about these true mirrors or whatever, because when you do look in a mirror, it's actually your, like you're looking at what looks like your right is actually your left, and so there's some people who think like you don't have a true sense of yourself because you're seeing the mirror image. So you can get mirrors that actually, like it goes through several reflective surfaces, and what you see is actually what other people would see when they look at you. Which apparently people feel like it looks a bit distorted because I guess most people aren't perfectly symmetric, so you're used to a certain view of yourself, and that's supposed to mess with you. I don't know. I haven't looked at one, so if anyone does, let me know. Anyway, recall from the law of reflection that states the angle of incidence is always equal to the angle of reflection. I would say like that one's kind of what you expect. The only real thing here, if we're looking at reflection, so we have an incident ray, and just a little bit of technical names to remember / review. The incident ray here is the ray that comes in. Incident means, right, it's where it starts. Then it reflects off the surface, and then we have a reflected ray. Right? And that is the normal, right? The term normal just means 90 degrees or perpendicular, right? They all mean the same thing. So the key to this, or the one thing to remember, it seemed to me kind of arbitrary when I remember learning this, because I did think like, well, why don't you measure the angle here, right? Why don't you measure the angle from the surface? But we don't, right? So that's just one of those little things to remember, so that if you get a really low angle of incidence, right, that just means it's going in very sharply here because the angle is measured relative to the normal. Right? So just something to sort of tuck in your brain while we're doing this stuff, and remember that. And that's sort of the whole point reflection right here, right? The angle of incidence equals the angle of reflection. Important, but worth noting, right? And so we have two types of reflection generally. We have this one here, which is generally what you think of when you think of reflection, probably, where we have a smooth surface, right? These are great, useful for mirrors and such. What about this one, referred to as diffuse reflection, right? So over here we had specular, just a name to remember, specular reflection, which just means it's off a smooth surface. And on the other hand here, we have diffuse reflection, right, which is off a rough surface. Does this seem like a good thing? I'm sort of kidding with you. It's a trick question, right? It depends on the circumstance. If you're making, let's say, paint for a wall, right, you probably want diffuse reflection, right? You don't want people like seeing themselves in it and really smooth reflection. And the whole idea, though, if you look at a diffuse reflection, it's still the angle of incidence is still the angle of reflection, right? It's just the surface itself is so rough that the light waves just really seem to get scattered, right, as they hit it. So, but if you look at any particular one, right, if you look at this light ray right here, right, the angle of incidence equals the angle of reflection. You could draw a normal to that surface, right, which is here, and that's what you would see. Similarly, you could do the same thing over here, right? You could look at this angle and you could say, yes, the angle of incidence equals the angle of reflection. There's a normal, right? Those two angles are equal, but because of the roughness of the surface, it goes everywhere. That's it. This is made as often desirable, right? You don't want a lot of reflection off of a lot of stuff, but sometimes you do. Sometimes this is a desirable thing. Maybe you want a nice, shiny car, or a mirror or something, right? So you want this. It just depends on the application. All right, we'll talk about refraction. I went and made these diagrams. Well, the top one I took, the second one I made from the first one by manipulating it. I realized I didn't get one of the tires there, probably the most important one. But now I'm looking, I'm like, you know what? I don't even really like it. I do, but we'll see. So what is refraction? So if we look at the phenomenon, we look at what happens. Okay, we see light bend. You can do this. get a glass, stick a straw in it, right? And it looks like, it bends, even though it doesn't. Why does it look that way? Well, because it refracts, right? So anytime you have light going from one surface to another, we know that there's three things that can happen, right? When light hits a surface, we can look right here. We can say, okay, this incident ray here hits the surface. Well, one, it can be reflected, which is, what you see here, and maybe some of the light is. Two, it can be transmitted through and or refracted, right? In this case, it's not just transmitted straight through, it's refracted because of this. The other is absorbed, in which case, game over. We don't really, need to think about it. So we're mainly concerned with reflected and refracted in this case, right? Because it's a different surface, it's not just transmitted through. And so for the top, right, the angle of incidence equals the angle of reflection. But for the refracted ray here, we've got to deal with theta 1 and theta 2. Now this is a bit of a complex phenomenon in some ways, but in terms of like looking at what happens here, the way we think of it is we say, well, okay, the speed of light is c, which roughly, 3 times 10 to the 8 meters per second in a vacuum, but it tends to slow down in some materials, right? And I just copied this out of a textbook, right? It gives you a bunch of speed of light in different media, I guess would be the plural. And you can see it slows down quite substantially, percentage-wise, in a lot of different materials. So I find that sort of the most helpful when I'm looking at refraction. So you can look at, if you're trying to see like, well, first of all, just what's going to happen. Do I expect this to bend toward the normal, which is what we're seeing here? So you can see in this example when light goes from air to glass, right? It doesn't proceed straight this way, right? It actually bends toward the normal, right? Remember, this is the normal here, right? The straight line through it. And so if you look at that in terms of, and think of it in terms of speed, so you can imagine, well, light is going through a faster medium into a slower. So what happens? And that's sort of like this. I find this picture here somewhat helpful. It's what I've always remembered. So light is on a faster surface. So picture like a wagon being pulled along something like pavement and then going into a slower surface. And I suppose if I was being a little better about this, I would say, like, forget about the two back wheels on this wagon. I feel like that sort of messes with it. So, like, forget about that part back here, right? Just imagine, like, you're pulling this two-wheeled wagon. You're holding it, so it's not going to fall over. And, so you only have the two front wheels. You hit the slower surface first, right? This wheel here hits the slower surface first. And so what happens, right? Well, the thing gets torqued around and it ends up going with this velocity here, you might say, right? You end up changing your direction of motion, right? And so you bend it toward the normal. Again, this being the normal, right? And if you go the other way, right, which is shown in this diagram here, where you're going from a slower surface into a faster one, what does refraction look like then? Well, that's sort of, again, imagine the wagon, and now I feel like this front wheel is really important here. Right, we got our front wheel here, and again, just sort of ignore the whole back of this wagon. We don't really need the back of this wagon. This is just, right, really this is just like a two-wheel little wagon that we're pulling, and this front wheel here hits this faster surface first, right? So it's gonna go faster, and that's gonna cause this thing to torque that way, right? The way that you're seeing the direction of motion here change. And that's exactly what you see here. So it's just always sort of that memory trick I had here. In terms of the specifics of it, you can use Snell's law here, which just says N1. And remember, N is the index of refraction. So when you see these in the equation, so N1 is the index of refraction of the first material. and theta 1 is the angle of incidence, and theta 2 is the angle of refraction, right? The angle in the second medium, and N2 then is just the index of refraction of the second material. You can put these together. Now, it may be that you're solving for any one of these things. You may be solving for N2 or solving for theta 2. So you just use the equation, put in the information you've got, and you can solve. And that's generally how it works. One thing to really, really remember about index of refraction is it's a little backwards. So it's written this way. Just remember that technically the index of refraction is the speed of light divided by the speed in the medium, right? This is the speed in the medium. Right? And you can also write this as the wavelength in medium 1 over the way. Like you can take this equation and manipulate it into this. And this is just because the frequency remains the same. So if a light goes into a different medium, the frequency remains the same. So if you have n equals, c over v, you could say, well, remember the speed is equal to f lambda divided by f lambda in the medium, right? And these just cancel out because the frequency remains the same in the medium. So you can always just use wavelengths as well as speeds. And since it's such an important number, I put the speed right there for you. The speed of light, and this is actually the definition now. This was the best measurement we have, but we now even define the meter itself, like the SI unit of the meter is defined as the distance light travels in 1 over 299,792,458 of a second, right? So this is the exact number for the speed of light. 299,792,458 meters per second. But as you can see, it's pretty good to just use 3 times 10 to the 8. I saw the thing there. So more generally, what is refraction? It is the bending of light when light goes from one medium to another. And note that it can bend toward the normal or away from the normal. Right? And the way we figure this out is by using this sort of index of refraction, which gives us the speed of the material. Now, normally, right, and this is where I was saying this whole thing is a bit backwards, so I get a bit off track. Normally, if you have something, right, you represent it as a fraction. So you would expect, and at least I would expect the index of refraction, n, to be the speed in the medium over c. Right? That's what I would kind of expect. And then I would expect to get a number that's some sort of a fraction, right, or decimal, right? So I might get a material that's like 0.9, another material 0.5. That tells me, oh, okay, the speed in that medium is half what it is in a vacuum, right? Remember, speed is the speed of light in a vacuum, like no particles in there. But this is the other way around. This is backwards, right? This is actually c over v. So that means if this is in a vacuum and v is c itself, then n is 1. So n equals 1 is in a vacuum. And if you're in any other medium, n actually increases, right? And that's why if you look at these things here, right? So remember, the index of refraction is the ratio of the speed of light in a vacuum to the speed of light in that medium. And so the numbers, so a bigger number actually means light is moving more slowly through that medium. I said it's one of those weird backwards things I kind of find. And you can see some typical numbers here just to, and you can see air, of course, as I mentioned, is practically a vacuum, right? It's there's not many. Now, there's seemingly a lot of particles of air here, right? I mean, if it weren't for air and the air pressure we have, you wouldn't be able to breathe, right? It gives you the pressure to force the air into your lungs and diffusion and all that. But compared to something like water, right, or even glass or whatever, right? These things are like 1,000 times more dense than air, right? It's just not really a comparison. So you see higher indices of refraction for these materials, and some actually getting quite low, like zircon here or something like that, where you're, down quite a bit. So remember, these bigger numbers, right? They actually mean light is moving more slowly. I put this bit at the bottom here just as a note, like full disclosure, it's a 4U class. So I do want to mention that technically, okay, light only appears to travel slower in different media. Light travels at the speed of light no matter what medium it's going through. It doesn't change. What actually happens is superposition, right? So you get some material here and you get light traveling through it, right? You get, let's say this is my light, this is my red light going through it, and it's being it's going through the material, it's not being absorbed. What happens? Well, there's electrons in all of the atoms here, so that sets up a response, right? This is an electromagnetic field that's changing and fluctuating as it goes through there. So that's creates a response field, if you will, right? So there's a field there, and what you actually see is the superposition of those two waves, which appears to travel slower. It doesn't actually. So just in the interest of full disclosure, I will tell you that. But for all intents and purposes, we will basically just go with the fact that we'll just say it slows down. We'll go with that, and we'll use that fact, even though that's not technically what's happening. But all the math and all the stuff, it does work out, right? That's often why we do what we do and simplify things, because it works. It gives us an equation, and then we can delve deeper and develop more, sophisticated and technical equations. Dispersion of light. Dispersion is just the separation of a wave into its component parts, right? So if you look at something like white light, right? Well, white light is just all the colors put together. It's the way you perceive it with your eye is it just sort of looks white, right? It's just all of them together. So we can use something like a prism to create this dispersion effect, right? And so what happens here is you can see you could draw a normal to this surface, and you could ignore all of this. You could just say, well, what happens when light hits that particular surface, right? Well, it goes more slowly in glass than in light, or that's the way we'll look at it. And so it bends toward the normal. Right? And then the opposite happens on the other side. When light exits this thing, we could look at the red light here, right? At this point here. And we could say, well, we could draw a normal to that surface. Right? And we could say, well, the light bends away from the normal. It's going into a faster medium, right? So it does that. Now, what happens, though, here is that technically that index of refraction, remember, I mentioned that the speed, or not the speed is the same, the frequency is the same, right? So whatever frequency it goes in with, it maintains, right? And so really it's the wavelength that affects this change, and different light, or what we can say is different colors, like have different wavelengths of light. Red has the longest wavelength, and violet light would have the shortest wavelength. And so it actually depends on the wavelength of light, how much it refracts, right? And so now, if you look up any of these things, or many of these questions we'll just give you one index of refraction for the medium, right? We'll just say that's it. But really, when you look at these values over here, right, that's just an average. And so we'll just use it because that really is the biggest determining factor in what the index of refraction is what the two materials are. But in fact, it does depend on the wavelength of the light going into it, And you can kind of see, if you look at one particular thing, like glass here, you can see that, well, if you have light that's about 400 nanometers, which would be like blue light, you could see, well, the index of refraction would be about 1.53. Versus if you had something closer to red light, which would be down here, which would have a little bit of a longer wavelength, so the effect wouldn't be as pronounced. You'd have an index of refraction of about 1.51. So we'll just average it out and say it's 1.52, and use that in any calculations we have, because really, like, there's not a big difference here relative to if we were using something like air, where we're just saying it's 1 and it's going into glass. Well, then we'll just say it's 1.51, and that'll be, sufficient for calculations. Okay, one more thing just to look at, because it's kind of a cool phenomenon. Total internal reflection. So we're talking about refraction. I always want to say refraction, but technically it's reflection, right? And you can see kind of an example of this happening here, where you've got light, trying to get out of this water, if you will, but instead of exiting the water, it's actually reflected back, right? And so how is this possible? Well, this is only possible when light is passing from a blank medium into a blank medium. I'll put it this way. I'll say it's only possible when light passes from, because it's just the easiest way for me to think of it, from a slower, so these are relative terms, into, or a, well, and technically it doesn't actually pass, right? Technically it stays in the slower medium. And the catch to this is, remember, when light goes from a slower medium into a faster medium, let me go back to that's this one here, right? It's like going from sand to pavement, right? It bends away from the normal, right? So you could look at a situation like this, where we have water and we have air. So you could say, okay, if I have light kind of like this, right? It's going to bend away from the normal. And this is just an approximation, right? So this would be, let me do that. This would be theta 1. This would be theta 2. And I guess I should draw like the light actually, so you can just see the direction, right? So then what happens if I keep increasing this angle? And I didn't really draw it, but you can imagine, like, if the angle was 0, right? If it was going straight, right, it would just go straight up. There's no angle of, right, angle of incidence. There's no angle of refraction, right? 0 is going to be 0. So then I get to something like this, right? But bend it a bit, and then I see it start to bend away. But then there's going to be some angle here where, you bugger, where it's actually going to go right along the surface. Right, where it's going to have a greater angle here, and it's going to go right. And so we refer to this here as the critical angle, right? This is the angle where you get nothing, right? It doesn't refract into the other surface. It doesn't reflect down, right? It's not actually reflecting. It just goes right along the surface, and so the light wave seems to just sort of disappear. And then, if I can delete that, and if you go beyond that, right, if you have any angle greater than, and I guess I should have labeled this here just for, let's call this, right, that's the actual critical angle, because we know the refracted angle is the 90. If you go beyond that, then you get, it just reflects. And so this is for theta 1 greater than theta c. And that's what we get.